Have you ever looked up at the night sky and felt that strange mix of wonder and unease, that quiet tug at the back of your mind, telling you there's something vast and unknowable just beyond the stars? The universe is full of mysteries that defy our wildest imaginations, some so bizarre, they seem ripped straight from science fiction. Consider this. Right now, you're hurtling through space at over 1,000,000 miles an hour, riding a tiny rock orbiting an average star in one of billions of galaxies. And yet, despite all we've discovered, the cosmos holds secrets that still leave scientists speechless. Like the eerie silence of the Fermi paradox, if the universe is so unimaginably large, why haven't we found a single trace of other civilizations? Or the unsettling fact that 95% of the universe is made of stuff we can't even see, touch, or comprehend. Dark matter, hidden dimensions, galaxies that defy physics, these aren't plot twists from a movie. They're real, and they're just the beginning. What if I told you everything you think you know about space might be wrong, that the truth is stranger, more dazzling, and at times more terrifying than anything we've been taught? Imagine staring into the void only to realize it's staring back, not with eyes, but with forces and phenomena so alien, they rewrite the rules of reality itself. Take black holes, for example. We picture them as cosmic vacuum cleaners sucking in everything nearby. But what if they're gateways or holograms or even alive? And then there's the Great Attractor, a mysterious gravitational force pulling entire galaxies toward it like some unseen puppeteer. No one knows what it is. No one knows where it leads. That's the universe we live in, one where every answer unravels 10 new questions, where the fabric of space and time might be nothing more than an illusion. This isn't just a story about stars and planets. It's a journey into the heart of existence itself, where the laws of physics bend and the impossible becomes routine. Over the next 30 revelations, we'll uncover truths that will make you question reality, from parallel universes hiding in plain sight to the shocking possibility that we might be alone in the cosmos after all. Some of these discoveries will fill you with awe. Others might keep you up at night, but one thing's certain, by the end, you'll never look at the night sky the same way again. So take a deep breath, because we're about to dive into the deepest, darkest, and most dazzling corners of the universe, and what we find there will change everything. Right now, as you watch this, an invisible hand is shaping the cosmos, not metaphorically, literally. The stars, planets, and galaxies we see, they're just floating specks in a vast ocean of something we can't see, can't touch, and barely understand. Scientists call it dark matter and dark energy, the twin ghosts that make up 95% of everything in existence. Think about that for a second. Every mountain, every ocean, every person you've ever met, all of it amounts to less than 5% of the universe. The rest is a mystery so profound, it redefines what we mean by reality. Picture the universe as a spiderweb, but one where the silk threads are invisible. Galaxies cling to these hidden strands, pulled into enormous clusters by forces we can't detect. This is the cosmic web, dark matter's secret architecture. Without it, galaxies would fly apart, stars would scatter, and the night sky would be empty. Yet despite holding the universe together, dark matter leaves no trace. It doesn't absorb light, reflect it, or emit any radiation we've found. It's like trying to catch smoke with your bare hands. So how do we know it's there? Imagine watching leaves swirling in a park on a windless day. You can't see the breeze, but the movement betrays it. That's how scientists first detected dark matter, by seeing its gravitational tug on stars and galaxies. Entire galaxies spin so fast that, by all rights, they should fling themselves apart. But something invisible grips them, an unseen anchor keeping the cosmos from unraveling. And then there's dark energy, even stranger. While dark matter pulls, dark energy pushes, accelerating the expansion of the universe like some anti-gravity force. Billions of years from now, distant galaxies will vanish over the cosmic horizon. not because they've moved, but because space itself is stretching faster than light can bridge the gap. The hunt for answers is on. Deep underground, in abandoned gold mines and beneath mountains, experiments like the LUX Zeppelin project wait in perfect darkness, hoping to catch a single particle of dark matter bumping into an atom. So far, silence, but if they succeed, it would rewrite textbooks overnight. Until then, we're left with a universe where nearly everything is hidden in plain sight, a reminder that what we see isn't just incomplete. It might be the smallest part of the story. Einstein once said time isn't the rigid, unchanging thing we think it is. It's more like a river, bending and twisting around the universe's heaviest object. Nowhere is this stranger than near a black hole where gravity warps time itself. Picture this: you're watching an astronaut drift toward the edge of a black hole's abyss. From your safe spot far away, their movements slow to a crawl, their spacesuit creaks in slow motion, their heartbeat stretches into deep, dragging thumps. But for them, time feels perfectly normal. Seconds pass like they always do, yet when they finally pull away, if they can, they'd return to a world where decades or even centuries have flown by without them. This isn't science fiction, it's the brutal reality of time dilation, a quirk of Einstein's general relativity. The closer you get to a black hole's monstrous gravity, the more time warps around you. Think of it like walking into syrup. Time thickens, slows, and eventually grinds to a near halt at the event horizon. The movie Interstellar got this eerily right with Gargantua, the black hole that cost Matthew McConaughey's character 23 years on a watery planet, just hours for him. That's the cost of playing near cosmic monsters, but here's where it gets wilder. Time doesn't just slow, it distorts. Near a black hole, the universe's clockwork fractures. Light bends so severely that if you could hover at the edge, you'd see the back of your own head. Light curves so far around the hole it loops back to you. And for any astronaut daring enough to approach, every tick of their wristwatch would stretch longer and longer until, from Earth's perspective, it stops entirely. They'd become frozen in time, a ghost in the cosmic machine. What does this mean for real space travel? Even our bravest explorers wouldn't survive the trip, but if they could, they'd return to an unrecognizable Earth. A 5-minute chat near a black hole could cost you lifetimes back home. It's the universe's cruelest time machine, one where you only travel forward, watching everything you love age without you. Yet this bizarre effect isn't just black hole theatrics. GPS satellites orbiting Earth have to account for tiny time wrinkles caused by our planet's gravity. Without those adjustments, your maps would be off by miles within minutes. So next time you check your phone's location, thank relativity and remember, time is anything but absolute. It's as flexible as the universe is strange. In the vast expanse of the cosmos, where galaxies cluster like cities and stars blaze in every direction, there's a place so empty it defies logic. Imagine a hole in the universe, not just any hole, but a gaping void 330 million light-years across, where galaxies are almost non-existent. This is the Boötes Void, a cosmic desert so eerily barren, it's been nicknamed the Great Nothing. If you were to teleport to its center, the night sky would be nearly pitch black, with only a handful of faint galaxies breaking the darkness. For comparison, our own Milky Way has dozens of galactic neighbors within just a few million light-years. But here, you'd be lucky to spot even one. How does something like this even exist? One theory suggests it's a statistical fluke, a cosmic accident where matter simply didn't clump together like it did everywhere else. But the numbers make that hard to swallow. The odds of nature carving out a void this massive by chance are astronomically low, like rolling 1,000 dice and getting all ones. Some scientists wonder if it's evidence of something far stranger. Could advanced civilizations have harnessed the energy of entire galaxies, leaving behind a wasteland? Or is the void a scar from an ancient collision between universes we can't yet comprehend? Then there's the spine-tingling possibility that the Boötes Void isn't empty at all. What if it's filled with something we can't see? Dark matter doesn't emit light, but it still exerts gravity. Could this void be packed with it, bending the fabric of space in ways we don't yet understand? Or worse, what if it's a glitch in the universe itself, a tear in reality where the rules we know simply don't apply? For now, the void keeps its secrets. Telescopes have spotted a few lonely galaxies drifting through it like ships lost at sea, but their presence only deepens the mystery. Why are they there, and why so few? Each one feels like a clue to a puzzle we're only beginning to piece together. One thing's certain, the Boötes Void isn't just a blank spot on the map. It's a screaming question etched into the cosmos, daring us to look deeper and wonder what else might be hiding in the dark. Look up at the moon tonight, and you're seeing an escape artist in slow motion. Right now, as it orbits Earth, our lunar companion is quietly slipping away about 3.8 centimeters every year. That's roughly the speed at which your fingernails grow. It might not sound like much, but over cosmic timescales, this gentle drift reshapes our sky in ways that would shock our ancestors. This cosmic tug of war comes down to tides. As Earth spins, its oceans bulge toward the moon, creating a gravitational drag that transfers energy. Think of it like a parent twirling a child holding a heavy backpack. The weight pulls their arms outward, slowing the spin. Over billions of years, Earth's rotation has slowed from 6-hour days to our current 24, while the moon has been pushed farther out. Ancient shellfish fossils confirm this. Growth rings in 900-million-year-old clams show Earth once had 420-day years. The math checks out, but here's the heartbreak for eclipse chasers. In about 600 million years, the moon will have drifted so far that it'll no longer perfectly cover the sun. Total solar eclipses, those spine-tingling moments when day turns to night and the solar corona blazes like a halo, will vanish forever. The last humans, or whatever evolves after us, will never know the awe of standing in the moon's shadow as it swallows the sun whole. Remarkably, we've caught this celestial getaway on camera, sort of. Apollo astronauts left mirrors on the moon, and scientists still bounce lasers off them to measure its retreat. Meanwhile, ancient Babylonian eclipse records from 3,000 years ago reveal subtle timing shifts that align perfectly with modern calculations. Their clay tablets, etched by scribes who feared eclipses as omens, now serve as scientific time capsules proving the moon's slow farewell. What happens next? The dance continues until Earth's rotation syncs with the moon's orbit, locking one side of our planet in eternal moonlight. But by then, the sun's death throes will have long since vaporized both worlds. For now, the moon's retreat is a silent reminder. Even the most constant things in our sky are temporary. Every eclipse you witness is a fleeting gift, a cosmic handshake across time that future civilizations will only read about in history's fading pages. Some stars mock the very age of the cosmos itself. Take HD 140283, nicknamed the Methuselah star, a faint dot in Libra that shouldn't exist. When astronomers measured its age, the numbers spat back an impossible verdict: 14.5 billion years. That's a full 700 million years older than the universe's estimated 13.8 billion years. It's like finding a grandfather clock that ticks time from before clocks were invented. How does this cosmic paradox happen? Blame the uncertainties of stellar archaeology. Determining a star's age isn't as simple as counting rings in a tree. Scientists analyze chemical composition, brightness, and motion, then plug the data into models of how stars evolve. But those models rely on assumptions, like the opaque interiors of stars where nuclear fusion cooks elements. If we've misunderstood how quickly certain reactions occur, or how metals disperse in aging stars, the math spirals into nonsense. The Methuselah star might simply be a case of bad cosmic accounting, its true age hidden behind layers of scientific guesswork. Yet there's a thrilling alternative. What if the star really is older than the universe? Some theories suggest physical constants like the speed of light or the strength of gravity might not be constant at all. They could have shifted over cosmic time, subtly altering how stars burn. If true, the Methuselah star might be a relic from when the laws of physics themselves were different. Even wilder, it could be an immigrant from another universe entirely, flung here through some crack in the multiverse. Imagine a star that remembers a different reality, carrying secrets from a cosmos that predates our own. Of course, Occam's razor favors measurement errors. Revised estimates now place the star's age just shy of the universe's, thanks to better data on its oxygen content, but the mystery lingers like a stubborn shadow. Every time we think we've pinned down the rules, the universe winks back with something that defies them. The Methuselah star isn't just an anomaly, it's a reminder that the cosmos still holds cards it hasn't shown us. And that's far more exciting than any tidy answer could ever be. Deep in the heart of the Milky Way, near a colossal cloud of gas called Sagittarius B2, astronomers made a discovery that sounds like something from a sci-fi bakery. The universe smells like raspberries. That's not poetic license, it's chemistry. The cloud is packed with ethyl formate, the same molecule that gives raspberries their sweet, fruity scent. If you could take a deep breath in that region of space and survive the lack of oxygen, radiation, and near absolute zero temperatures, the aroma would hit you like a cosmic dessert cart. But this isn't just a quirky cosmic fact, it's a clue to something far grander. Ethyl formate is just one of thousands of complex molecules floating between the stars. Alcohol, sugar, even amino acids, the building blocks of life, are all out there, forged in the hearts of dying stars and scattered across the galaxy by stellar winds and supernova. Imagine the universe as a vast, chaotic kitchen where supernova act like blenders, mixing ingredients, and nebulae serve as ovens, slowly baking them into more complex compounds. Here's where it gets mind-blowing. These molecules don't just linger in space. They hitch rides on comets and asteroids, eventually raining down on young planets like Earth billions of years ago. That glass of wine you sip, the sugar in your coffee, the very DNA coiled inside your cells, their raw ingredients might have been cooked in the cores of ancient stars, then delivered to our planet by celestial couriers. We're not just made of stardust, we're made of flavored stardust. Of course, space isn't only raspberry-scented. Other regions reek of rotten eggs thanks to hydrogen sulfide or bitter almonds courtesy of cyanide. But the sheer variety of organic molecules out there suggests something extraordinary. The universe isn't just hospitable to life, it's prepping for it like a gardener scattering seeds. So next time you bite into a raspberry, remember, you're tasting a molecule that's been drifting through the cosmos for eons, a tiny fragment of the universe's endless, invisible recipe book. And somewhere out there, another cloud might be brewing the next great flavor of existence, one we haven't even dreamed of yet. If you could crack open the universe's treasure chest, you'd find a planet that puts every jewelry store on Earth to shame. Meet PSR J1719-1438b, a world so dense with crystallized carbon, astronomers suspect it's literally made of diamond. Orbiting a pulsar 2,000 light-years away, this exotic exoplanet is the remnants of a dead star, crushed into something stranger than fiction. Picture a world where rain isn't water but molten graphite, where mountains might gleam with diamond peaks, and the very ground beneath your feet could be a single, continuous crystal lattice. The physics behind this is surreal. When the planet's precursor star collapsed, its carbon-rich core was squeezed with such unimaginable pressure that carbon atoms locked into diamond structures. Under that kind of force, even something as mundane as carbon becomes a cosmic jewel. Now for the fun part, just how much diamond are we talking about? If you could mine this planet, which, let's be clear, you can't, it's tidally locked to a spinning corpse of a star that bathes it in deadly radiation. Conservative estimates suggest its diamond core could outweigh Earth's entire economy. Try to wrap your head around that. The Hope diamond, the crown jewels, every engagement ring ever sold, they'd all be specks of dust compared to this celestial motherlode. But here's the twist. Diamonds aren't rare in the universe. They're only precious here because we treat them that way. On PSR J1719-1438b, they're as common as dirt, literally. And that flips everything we think about value on its head. What if, somewhere out there, civilizations trade in something we consider worthless, like hydrogen or nitrogen? Our most prized possessions might be cosmic sidewalk rubble. The real magic of this planet isn't its sparkle, it's the way it shatters our assumptions. A diamond the size of a world isn't just a geological oddity. It's a reminder that the universe doesn't play by our rules, doesn't share our economies, and doesn't care what we find beautiful. Out there, in the infinite dark, there are wonders that make even kings and billionaires look small, and that's the most humbling gem of all. That beam of sunlight warming your skin right now. It's older than human civilization by a lot. The journey of a single photon from the center of the sun to Earth is a cosmic odyssey that would make Homer's epics look like a quick stroll. Picture this, deep in the sun's core, where temperatures hit a blistering 27 million degrees, hydrogen atoms fuse into helium in a nuclear furnace. The energy released creates photons, particles of light, but here's the kicker: these newborn particles don't zip straight out into space. They embark on a chaotic obstacle course that lasts a staggering 100,000 years. Think of it like trying to walk through a packed stadium during halftime. The sun's interior is so dense that photons can't travel more than a fraction of an inch before slamming into another particle. They bounce around like microscopic pinballs, zigzagging at random angles. Each collision sends them careening off in a new direction, sometimes forward, sometimes backward. Over time, they slowly, painstakingly work their way outward through the radiative zone, where matter is so tightly packed that light effectively crawls. By the time photons reach the sun's outer layers, the convective zone, they've endured trillions of collisions. Here, hot plasma churns like boiling soup, finally carrying them to the surface like bubbles rising in a lava lamp. When they finally break free at the photosphere, that last leg of their journey to Earth, a breezy 8 minutes and 20 seconds. That's right. After spending millennia trapped in an atomic maze, light crosses the 93 million miles to your backyard in less time than it takes to brew a pot of coffee. What makes this even wilder? The sunlight you're seeing now was born when woolly mammoths still roamed the Earth. The photons hitting your skin began their journey before the first human settlements, before agriculture, before written language. They've been trapped in an endless atomic pinball game while pyramids were built, empires rose and fell, and your ancestors lived entire lifetimes. This mind-bending timescale reveals the sun's true nature, not just a ball of fire, but an unimaginably dense cosmic filter. If our star were less packed, light would escape faster, but it would also burn out sooner. That 100,000-year crawl is what keeps the sun shining steadily for billions of years, gifting Earth with the perfect, gradual trickle of energy that makes life possible. So next time you feel sunlight on your face, remember, you're not just touching space, you're touching deep time. The idea that space is a silent vacuum is one of the biggest misconceptions about the cosmos. Out there, beyond our atmosphere, the universe is alive with sound waves of charged particles dancing through magnetic fields, eerie wails echoing around planets, and chorus-like hums that could score a sci-fi horror film. The catch: these sounds aren't audible to human ears until scientists translate them into something we can hear. Take Earth's magnetosphere, the invisible magnetic shield protecting us from solar wind. When the Voyager probes skimmed its edges, they picked up something spine-tingling. Electromagnetic waves rippling through plasma converted into audio. They sound like ghostly birdsong at dawn. Scientists call these chorus waves, not because they're melodic, but because they rise and fall in frequencies that mimic a dawn chorus of birds. But there's nothing peaceful about their origin. These waves are born from violent solar storms where charged particles spiral along magnetic field lines, vibrating like plucked guitar strings. Then there's Venus, the planet often called Earth's evil twin. When the European Space Agency's Venus Express orbiter tuned into its magnetosphere, it captured something even stranger: whistler waves. These aren't the cheerful toots of a referee's whistle. They're bursts of radio waves generated by lightning cracking through Venus's thick, acidic clouds. Converted to sound, they're like phantom radio static from a station you can't quite tune in, crackling across millions of miles. So why does this matter? These sounds aren't just cosmic curiosities, they're vital clues to understanding space weather. Chorus waves, for instance, can accelerate particles to near light speeds, creating killer electrons that threaten satellites and astronauts. By listening to these eerie signals, scientists can predict solar storms, much like meteorologists track hurricanes. And those Venusian whistlers, they hint at how lightning behaves in alien atmospheres, helping us decode the chaotic skies of exoplanets light years away. Here's the wildest part: if you could stand in space without dying, you wouldn't hear any of this. Space is still a near-perfect vacuum, meaning sound waves as we know them can't travel. These sounds are actually electromagnetic vibrations picked up by probes and translated into frequencies our ears can process. It's like holding a stethoscope to the universe's chest, listening to the heartbeat of invisible forces. Next time someone says space is silent, you'll know better. The cosmos isn't mute, it's a symphony of plasma, a cacophony of charged particles, humming tunes we're only beginning to understand. And with every eerie chorus and phantom whistle, we're not just hearing the universe, we're decoding its secrets one vibration at a time. Somewhere in the darkness beyond our galaxy, a cosmic puppeteer is pulling the strings of our fate. 220 million light-years away lies the Great Attractor, a gravitational anomaly so powerful. It's dragging the entire Milky Way and thousands of neighboring galaxies toward it at 14 million miles per hour. This isn't just a gentle nudge, it's a full-blown cosmic current, sweeping us through the universe like leaves caught in a river's relentless flow. What makes this mystery even more tantalizing is its hiding spot. The Great Attractor lurks behind what astronomers call the zone of avoidance, an area of the sky obscured by the thick dust and stars of our own galaxy's disk. It's like trying to peer through a snowstorm to spot a distant mountain. For decades, this region was astronomy's blind spot, a frustrating blank space on the map where answers should be. Even now, with advanced telescopes, we're still squinting through cosmic fog to glimpse what's pulling us. But here's where the plot thickens. The Great Attractor isn't just some lone, supermassive oddity. It appears to be part of something far larger, an immense supercluster of galaxies called Laniakea, Hawaiian for immense heaven. This sprawling cosmic metropolis spans 500 million light-years, with the Great Attractor acting like its downtown core, exerting gravitational influence over everything in its neighborhood. Picture a colossal spiderweb with galaxies strung along invisible threads, all converging toward this unseen heart. What could possibly have this much gravitational muscle? The leading theory points to an unfathomable concentration of mass, perhaps a dense knot of dark matter, or a cluster of galaxies so vast it bends the fabric of space around it. But there's a twist. The Great Attractor's pull is even stronger than it should be, given the visible matter we've detected. Some speculate there might be something beyond it, an even greater structure like the mysterious Shapley supercluster tugging on the Great Attractor itself. It's a cosmic game of tug-of-war, and we're caught in the middle. The future of this enigma lies in next-generation telescopes. Instruments like the Square Kilometre Array, with its unparalleled sensitivity to radio waves, may finally pierce the zone of avoidance, revealing the Great Attractor's true nature. Until then, it remains one of the universe's most humbling puzzles, a reminder that even as we hurtle toward it, we still don't know what it actually is. So the next time you gaze at the night sky, remember this: we're not just orbiting the sun or drifting through the Milky Way. We're passengers on a much grander voyage, pulled toward a shadowy destination whose secrets are still waiting to be uncovered. And that journey toward the unknown heart of our cosmic neighborhood is far from over. At the heart of a cosmic car crash, nature forges some of its most extreme objects, neutron stars. These stellar corpses pack the mass of our entire sun into a sphere no wider than Manhattan, creating densities so absurd they defy common sense. A single sugar cube's worth of this material would weigh 1 billion tons on Earth. But that's not even the most shocking part. Some of these ultra-dense remnants spin faster than your kitchen blender, up to 700 rotations every second. Picture this: a city-sized object heavier than anything you've ever imagined, whirling so fast its surface moves at nearly a quarter the speed of light. The forces at play here are beyond extreme. If you stood on its surface and somehow survived the gravity that would flatten you into atomic paste, the centrifugal force would launch you into space like a slingshot. These rapid spinners are called millisecond pulsars, and they serve as the universe's most precise clocks, beaming radiation like interstellar lighthouses with a regularity that rivals atomic timekeeping. So how does a dead star end up spinning this fast? It's a violent cosmic heist. When a neutron star orbits a companion star, its monstrous gravity can steal material from its neighbor. As that stolen gas spirals onto the pulsar, it transfers angular momentum, like a figure skater pulling in their arms to spin faster. Over millennia, this process can accelerate the pulsar from a few rotations per second to hundreds, creating nature's ultimate centrifuge. But the real magic lies in what these spinning monsters do to spacetime itself. Einstein predicted that massive accelerating objects would ripple the fabric of reality, sending out gravitational waves. Neutron stars confirm this in spectacular fashion. When two of them collide, the resulting gravitational waves detected by observatories like LIGO jostle Earth by less than the width of an atomic nucleus. Yet we can measure it. That's how powerful these events are. Even more mind-bending, the spin of a lone pulsar can warp spacetime around it so severely that light following the curvature creates frame dragging, twisting space like honey stirred by a spoon. These celestial speed demons aren't just cosmic oddities. They're laboratories for physics we can't replicate on Earth. Their extreme conditions let us test general relativity, study the behavior of matter crushed beyond recognition, and even map the galaxy using their clock-like pulses. Next time you hear a blender's whir, think of neutron stars, nature's ultimate spin class, where the workout bends the universe itself. Here's a fact that will make you look at the next tree you pass in a whole new light. There are more trees on Earth than stars in our entire galaxy. Let that sink in for a second. Our planet is home to roughly 3 trillion trees, yes, trillion with a T, while the Milky Way, with all its swirling arms and glittering splendor, holds just 100 to 400 billion stars. That means for every single star in our galaxy, there could be anywhere from 7 to 30 trees right here under our feet. Think about what that says about Earth. We're living on a planet so lush, so teeming with life, that even the grandeur of our cosmic neighborhood pales in comparison. Picture a single oak tree in your backyard. Now imagine it multiplied 3 trillion times over, covering continents, climbing mountains, lining riverbanks. That's the staggering abundance we're talking about. And yet, for all that green, forests still only cover about 30% of Earth's land. The rest is deserts, ice, cities, places where trees can't take root. Just imagine if they could. But here's the cosmic punchline. This mind-boggling number is still a drop in the universe's bucket. While 3 trillion trees might outshine our galaxy's stars, the observable universe holds an estimated 2 trillion galaxies. Suddenly, those 3 trillion trees feel humblingly small. It's a paradox of scale. Our planet is unimaginably rich by local standards, yet vanishingly insignificant in the grand tapestry of creation. There's poetry in that. We spend so much time staring up at the stars in awe, but right beneath us is a hidden wilderness just as worthy of wonder. Those trees are more than just silent giants. They're Earth's lungs, its climate regulators, its ancient archivists. Some bristlecone pines have been alive since the pyramids were built. The oldest known tree, a spruce in Sweden, has roots stretching back nearly 10,000 years. That's older than human civilization itself, yet this abundance isn't guaranteed. Despite the staggering number, humans have cut down nearly half the world's trees since the dawn of agriculture. Forests that once seemed infinite are shrinking, and with them, the very balance that makes Earth so uniquely alive. When you realize those 3 trillion trees are the legacy of billions of years of growth and just a few centuries of destruction, the numbers stop feeling abstract. They become a call to action. So next time you walk through a forest, remember, you're standing in something rarer than a galaxy, a place where the universe, for all its infinite stars, chose to make life thick. And that's a miracle worth protecting. The universe isn't just expanding, it's doing so at breakneck speed, as if some unseen hand is pressing harder on the cosmic gas pedal with every passing moment. This startling revelation earned scientists the Nobel Prize in Physics in 2011, not just for discovering the expansion itself, but for showing that it's accelerating. And the culprit behind this runaway cosmic sprint, a force so mysterious we've only named it out of frustration: dark energy. Picture the universe as a loaf of raisin bread baking in an oven where galaxies are the raisins. As the dough expands, the raisins move apart, but in this case the oven keeps getting hotter, the dough keeps stretching faster, and eventually those raisins won't just drift, they'll be torn apart. The implications are as haunting as they are profound. Right now, galaxies beyond our local group are already slipping away, their light stretched into invisibility by the relentless stretching of space itself. But in the far future, this acceleration will reach a point where even the closest neighbors vanish. Imagine waking up one day to find every star outside the Milky Way gone from the sky, not because they've moved, but because the space between us has stretched so much that their light can no longer bridge the gap. Civilizations born in that era will gaze into a void and see nothing but darkness, their telescopes revealing only the ghostly echoes of a universe that once was. They'd have no way of knowing galaxies ever existed beyond their own. How do we know this is happening? It all traces back to supernova exploding stars that serve as cosmic mile markers. In the late 1990s, astronomers noticed these stellar explosions in distant galaxies were fainter than expected, as if space itself had stretched more than predicted during the light's journey to Earth. The conclusion was unavoidable. Expansion wasn't slowing down as gravity's pull should dictate. It was speeding up. Dark energy, whatever it is, appears to be stronger than gravity on cosmic scales, an anti-glue prying the universe apart. But here's the twist: we still don't know what dark energy actually is. The leading theory suggests it's a property of space itself, empty vacuum exerting repulsive force, growing stronger as the universe expands. Another idea posits it's an entirely new force field, one we've yet to describe. And then there's the spine-chilling possibility that our understanding of gravity is fundamentally wrong, that Einstein's equations break down over cosmic distances. Whatever the answer, dark energy is rewriting the universe's fate. The bleakest scenario, the so-called Big Rip, where dark energy's push becomes so dominant that it doesn't just separate galaxies, it shreds them. Stars, planets, even atoms could be torn apart in a final, violent crescendo of expansion. Thankfully, this nightmare scenario remains speculative. More likely, we'll face a slow fade where galaxies outside our local group blink out one by one, like lights dimming in a house we'll never leave. For now, we're lucky. We live in a golden age of cosmology where the night sky still brims with evidence of the universe's grandeur. But dark energy's silent work continues, carrying us toward a future where the cosmos forgets its own history. The lesson: the universe isn't just stranger than we imagine, it's stranger than we can imagine, and its final act may be the most mysterious of all. At first glance, Mercury seems like the last place you'd ever find ice. This scorched world, orbiting closer to the Sun than any other planet, bakes in daytime temperatures hot enough to melt lead, reaching a blistering 800 degrees Fahrenheit. But turn your gaze to its poles and you'll stumble upon one of the solar system's great paradoxes. Deep within certain craters, hidden from the sun's relentless glare, lies frozen water. These shadowy sanctuaries exist because Mercury's axis has almost no tilt. Imagine a spinning top perfectly upright, its poles never lean toward or away from the sun. As a result, some crater floors near the poles are permanently bathed in darkness, creating natural freezers where temperatures can plummet to -370 degrees Fahrenheit. Sunlight never touches these pockets, allowing ice to survive just a few steps away from furnaces capable of vaporizing metal. But how did water get there in the first place? The leading theory points to cosmic hitchhiker's comets and water-rich asteroids that bombarded Mercury over billions of years. Each impact delivered tiny amounts of water vapor, which migrated toward the poles and settled in these frigid traps. Over time, the ice built up layer by layer, like frost accumulating in the back of a forgotten freezer. Radar observations from Earth first hinted at this in the 1990s, but it wasn't until NASA, a messenger probe, orbited Mercury in 2011 that we got definitive proof. The spacecraft detected telltale hydrogen signatures in those shadowed craters, confirming what seemed impossible: ice on a planet that's practically inside a solar oven. What does this mean for the future? Mercury's ice holds clues for colonizing other worlds. The Moon, for instance, has similar permanently shadowed craters at its poles, cold traps that likely harbor ice of their own. Future lunar explorers could mine this ice for drinking water or split it into hydrogen and oxygen for rocket fuel. Mars, too, has vast underground glaciers beneath its dusty surface. If Mercury, of all places, can cling to water, it's a reminder that even the harshest environments might hide the resources we need to survive beyond Earth. Here's the real kicker: Mercury's ice might be older than the solar system itself. Some of those impacting comets could be time capsules from the cloud of gas and dust that birthed our sun, carrying water forged in interstellar space. So when we one day mine those shadowed craters, we might not just be grabbing a drink, we could be sipping on a relic from the dawn of the cosmos. It's a humbling thought. The universe stashes its treasures in the unlikeliest places, hiding frozen time capsules in the last spot we'd think to look. And if a sun-blasted hellscape like Mercury can cradle ice, what other surprises are waiting in the dark corners of our solar system? Venus doesn't just break the rules, it flips them upside down. While Earth takes a brisk 24 hours to spin on its axis, Venus drags out its rotation for a sluggish 243 Earth days. That's longer than its entire year, which zips by in just 225 days. Imagine living on a world where the sun rises and sets just twice in your lifetime, and where your birthday comes around before you've even had a single full-day night cycle. But the strangeness doesn't stop there. Venus spins backward. Unlike every other planet in the solar system except Uranus, it rotates clockwise when viewed from above, as if some cosmic hand reached down and flipped it like a pancake. This retrograde rotation turns the planet's sky into a surreal spectacle. The sun would rise in the west and set in the east, creeping across the heavens at a snail's pace. Theories about how Venus became this topsy-turvy world range from ancient catastrophes to gravitational ballet. One leading idea suggests a colossal collision, billions of years ago, knocked the planet into its backward spin, like a billiard ball struck with enough force to reverse its motion. Another possibility is that tidal forces from the sun's gravity, combined with Venus's thick, soupy atmosphere, gradually slowed and reversed its rotation over eons. And speaking of that atmosphere, it's in on the rebellion too. While Venus itself spins painfully slow, its atmosphere whips around the planet at hurricane speeds, circling the globe every 4 days. This super-rotation creates winds that scream at 220 miles per hour faster than the planet beneath them rotates. It's like watching a blender lid spin independently of the jar, churning clouds of sulfuric acid into a permanent planet-wide tempest. What does this mean for Venus's surface? Picture a landscape where the air is thick enough to crush submarines, where the heat could melt lead, and where the winds overhead rage like a perpetual storm, but down on the ground the air is eerily still. A visitor might stand in deafening silence, watching the poisonous clouds race overhead, while the sun lingers on the horizon for months at a time. This bizarre mismatch between rotation and orbit isn't just a curiosity, it's a cautionary tale about how chaotic planetary evolution can be. Venus shows us that even worlds born from the same stellar nursery as Earth can end up as mirror image oddballs, spinning backward while their skies outrace them. And somewhere out there, another planet might be waiting to surprise us with even stranger tricks. Even the most reliable cosmic measuring sticks sometimes disagree, and when they do, entire theories tremble. Right now, astrophysics is wrestling with a problem so stubborn they've called it the Hubble tension. At its heart lies a simple question: how fast is the universe expanding? You'd think we'd have that nailed down by now, but 2 of science's most trusted methods keep giving different answers, and the gap between them is growing wider, not smaller. The first method leans on the cosmic microwave background, the afterglow of the Big Bang. The Planck satellite, Europe's premier space observatory, mapped this ancient light with exquisite precision, using tiny temperature fluctuations to calculate the universe's expansion rate. Its verdict: about 67 kilometers per second per megaparsec. Translation: for every 3.3 million light-years you look deeper into space, galaxies appear to recede 67 kilometers per second faster. But then there's the second approach, tracking exploding stars called Type 1a supernova. These stellar detonations are so uniform in brightness, they're called standard candles, letting astronomers gauge cosmic distances like mile markers on a highway. When teams like the Nobel-winning Supernova Cosmology Project used them to measure expansion, they got a different number: 73. That 6-kilometer gap might seem trivial, but in a field where decimal points matter, it's a chasm. Here's why this rift rattles physicists. Both methods are rock solid in their own realms. Planck's data from the infant universe is impeccable. Supernova observations from telescopes like Hubble are equally robust. Yet they disagree by enough to suggest something's missing from our models, maybe something monumental. The leading fixes sound like sci-fi plot twists. Could an unknown form of dark radiation, an ultra-fast particle from the Big Bang, have tweaked the early universe's expansion? Or is dark energy weirder than we thought, changing strength over time like a dimmer switch? Some even speculate gravity itself might behave differently across cosmic epochs, bending the rules Einstein laid down. This isn't just academic quibbling. The Hubble constant isn't just a number. It's the yardstick for the universe's age, its fate, its very architecture. If we've misjudged it, we might be looking at the cosmos through a warped lens. Next-generation telescopes, like the James Webb Space Telescope, are already diving into this mystery, hunting for hidden variables in the light of ancient galaxies. For now, the tension remains, and that's exhilarating. Science thrives where answers dissolve into questions, where the universe reminds us it still holds cards close to its chest. Whether the solution is a new particle, a tweak to relativity, or something no one's dreamed up yet, one thing's certain: the cosmos isn't done surprising us. Saturn wears a crown unlike any other in the solar system, a swirling, six-sided storm so precise it looks carved by some celestial machine. This massive hexagon, wider than 2 Earths stacked side by side, has churned over Saturn's north pole for at least 4 decades, maybe longer. Imagine a hurricane with razor-straight edges spinning at over 300 miles per hour, its geometric perfection defying everything we know about fluid dynamics. NASA Cassini spacecraft gave us our first jaw-dropping close-ups of this atmospheric enigma. The images revealed a honeycomb of clouds, sharp, angled, and unwavering, like a colossal snowflake etched into Saturn's skies. Unlike earthly storms, which rage chaotically before dissipating, this hexagon is a model of stability, a permanent fixture on a planet where winds scream faster than bullets. So how does nature sculpt something so unnaturally precise? The leading theory points to standing waves, vibrations in Saturn's jet stream that lock into a hexagonal pattern, much like how a guitar string vibrates at fixed frequencies. On Earth, similar patterns can appear in lab experiments with spinning fluids, but they're fleeting and tiny. Saturn's version scales up to planetary proportions and refuses to fade, sustained by the planet's mind-bending rotational speed and lack of solid obstacles like mountains or continents to disrupt the flow. Yet even our best simulations fall short. Labs can't recreate the sheer scale or stamina of this storm, leaving scientists to wonder if other forces, like deep-rooted convection currents or interactions with Saturn's magnetic field, are at play. Some even speculate the hexagon might be a kind of shadow cast by turbulence deeper in the planet's liquid metallic hydrogen core, a three-dimensional structure projecting its shape onto the visible atmosphere. What makes this storm even more mesmerizing is its seasonal persistence. As Saturn orbits the Sun, its poles endure decades-long winters shrouded in darkness. Yet the hexagon endures unaffected by the absence of sunlight or the planet's extreme axial tilt. It's as if the storm exists in its own pocket of physics, playing by rules we haven't fully decoded. Cassini's final glimpses before its mission ended in 2017 showed the hexagon's vibrant hues shifting with Saturn's seasons, its blues and golds morphing like a cosmic mood ring. But the shape itself remained, a testament to the universe's ability to craft order from chaos. For now, this six-sided marvel remains one of the solar system's most hypnotic puzzles, a reminder that even the giants among planets still guard secrets we're only beginning to unravel. At the smallest scales imaginable, where distances shrink to a millionth of a billionth of a billionth of a meter, space-time itself stops behaving like the smooth fabric we picture. Instead, it becomes a seething, frothing chaos, a quantum foam where particles blink in and out of existence in bursts of raw energy. This isn't just theoretical poetry. These microscopic bubbles of reality are constantly forming and dissolving, like the foam on a stormy ocean, revealing a universe far wilder than our eyes can see. The key to this frenzy lies in Heisenberg's uncertainty principle, which allows particles to borrow energy from nowhere so long as they vanish quickly enough. On this scale, spacetime isn't just bent or warped, it's alive, a turbulent sea where virtual particles flicker into being, collide, and annihilate in fractions of a nanosecond. Picture the static on an old TV screen, but instead of random noise, those flickers are entire particles and antiparticles dancing in and out of reality. Now here's where it gets truly mind-bending. Some theories suggest these quantum fluctuations might not just be noise. They could be the key to unlocking wormholes, those hypothetical shortcuts through spacetime. Imagine 2 points in the quantum foam briefly connecting, forming a microscopic tunnel between distant regions of the universe. Under normal circumstances, these tunnels would collapse instantly, crushed by the same forces that created them. But what if we could stabilize them? Some models of quantum gravity hint that with enough energy, or the right manipulation of spacetime, these fleeting wormholes could be stretched, reinforced, and even navigated. This isn't just science fiction. Physicists like Miguel Alcubierre have proposed theoretical warp drives that exploit similar principles, bending spacetime to create a bubble where the fabric of reality moves around a ship rather than the ship moving through space. The catch: it would require energy densities on par with collapsing stars, and control over forces we're only beginning to understand. But the quantum foam suggests the raw material might already be there, woven into the universe's smallest seams. Could this foam also hold clues to time travel? Some interpretations of quantum mechanics suggest particles hopping backward through time might already be happening in these fleeting fluctuations. If we could isolate and amplify those effects, the implications would rewrite physics and human history. Of course, the challenges are staggering. The Planck scale is so infinitesimally small that probing it directly is beyond our current technology. Even the most advanced particle colliders are like trying to study a snowflake with a bulldozer. Yet the tantalizing possibility remains. The universe's tiniest, most chaotic layer might be its most revolutionary. What looks like random noise today could be the foundation of tomorrow's breakthroughs, where wormholes, warp drives, and even time machines aren't just dreams, but engineering challenges waiting for the right minds to solve them. The quantum foam doesn't just redefine emptiness, it whispers that the universe is far stranger and far more malleable than we ever dared to imagine. The moon has been Earth's silent companion for billions of years, hanging in the sky like a familiar friend. But turn it around and you'll find a face so different, it might as well belong to another world. The side we always see is smooth, dotted with dark patches we've named seas, though they're actually ancient lava plains. But the far side, it's a battered wasteland, pockmarked with craters, jagged mountains, and hardly any of those smooth basins. It's as if the moon spent its entire existence with one cheek turned toward us, hiding its scars in shadow. Why such a stark divide? The answer might lie in a cataclysmic past. The leading theory, the giant impact hypothesis, suggests that shortly after the moon formed, it was still molten and vulnerable. Around 4 billion years ago, a dwarf planet or massive asteroid could have slammed into the far side, blasting away crust and leaving behind a war zone of craters. Meanwhile, the near side, shielded by Earth's gravity, remained relatively unscathed. But here's the twist: the impact wouldn't just leave scars, it would trigger volcanic eruptions. As magma bubbled up from the moon's interior, it flooded the near side's lowlands, creating those smooth, dark plains we now call Maria. The far side, already stripped of its crust, never got that same resurfacing. Earth didn't just stand idly by during this process. Our planet's gravity likely played a role in shaping the moon's asymmetry, acting like a cosmic sculptor. The near side's crust may have been pulled slightly thinner by Earth's tidal forces, making it easier for lava to breach the surface. Meanwhile, the far side, facing away, cooled and hardened into a thicker, more rigid shell, one that couldn't hide its violent history. For decades, the far side remained a mystery, hidden from Earth's gaze. Then came China's Chang missions, the first to land and explore this rugged terrain. Chang 4 in 2019 touched down in the Von Karman crater, revealing a landscape unlike anything we'd seen before. Boulders jutted like broken teeth. The soil was finer, dustier, and laced with minerals that hinted at the moon's violent past. Even more fascinating, the far side's crust is thicker, up to 12 miles deeper in places, supporting the idea that it endured a brutal pummeling while the near side got off easy. What does this duality teach us? The moon isn't just a dead rock. It's a time capsule of the solar system's chaotic youth. Those two faces tell a story of violence and healing, of how a cosmic collision and Earth's gentle pull shaped a world forever bound to ours. And as we keep uncovering its secrets, we're reminded that even the most familiar objects in the sky still have mysteries waiting in the dark. Deep in the constellation Centaurus, a ghostly bow tie of gas drifts through space, holding a record that would make even Pluto shiver. The Boomerang Nebula isn't just cold. It's the coldest natural place we've ever found in the entire universe, with temperatures plunging to a bone-numbing -458 degrees Fahrenheit. That's just 1 degree warmer than absolute zero, the theoretical point where all molecular motion stops. To put that in perspective, even the vast emptiness between galaxies isn't this frigid. The cosmic microwave background, the afterglow of the Big Bang, hovers at a balmy -455 degrees. The Boomerang Nebula is colder than space itself. So how does this cosmic deep freeze happen? The secret lies in the nebula's suicidal expansion. A dying star at its heart is shedding material at breakneck speeds over 300,000 miles per hour, creating a wind so violent it acts like an interstellar air conditioner. As the gas expands outward, it cools dramatically, the same way spraying compressed air from a can chills your fingers. But here's the twist: this nebula isn't just expanding fast, it's doing so in a way that maximizes cooling. The gas flows outward in a precise, symmetrical pattern, like a pair of icy wings, ensuring minimal heat gets trapped. The result: a natural refrigerator operating on a cosmic scale. And yet, as extreme as the Boomerang Nebula is, it's not quite as cold as what we've achieved in labs. In places like MIT and the University of Bremen, physicists have used lasers and magnetic fields to chill atoms to within billionths of a degree above absolute zero, creating conditions so bizarre, matter starts behaving like waves rather than particles. These experiments reveal quantum phenomena that simply can't exist in nature, like Bose-Einstein condensates, where atoms merge into a single quantum state. But here's the catch: while we can out-chill the Boomerang Nebula in tiny, controlled volumes, we've never cooled an entire nebula-sized expanse to such extremes. Nature still holds the record for the biggest deep freeze. What makes the Boomerang Nebula even more fascinating is its fate. This ultra-cold phase won't last forever. As the dying star's core heats up, it will eventually ionize the surrounding gas, causing the nebula to glow as a planetary nebula, a fate shared by stars like our Sun. For now, though, it's a fleeting monument to nature's ability to push limits we didn't think possible. A place where the void isn't just empty, but actively cold, a cosmic reminder that even in the vast heat of creation, there are pockets of perfect chill. The night sky might seem like a crowded place, but the universe plays a cruel trick on our eyes. Those glittering dots are so far apart, even when entire galaxies collide, trillions of stars dancing in cosmic slow motion. The chances of two stars actually hitting each other are almost zero. Picture two massive crowds running through each other in an endless stadium where every person is miles apart. That's what's coming when the Milky Way tangles with Andromeda, our closest galactic neighbor, in about 4.5 billion years. Computer simulations of this future crash reveal something breathtaking: a swirling ballet of gravity and light where stars pirouette past one another like skaters avoiding collisions in an impossibly vast rink. The sheer scale of space is staggering. Even when galaxies merge, the average distance between stars is so vast, about 5 light-years in our galactic neighborhood, that direct impacts are rarer than winning the lottery 1,000 times in a row. Instead, gravity does something far more elegant. As the galaxies intertwine, their stars get flung into new orbits, stretched into long tidal streams, or even ejected entirely into the void between galaxies. Here's the best part: our solar system will probably survive the chaos completely unharmed. The Sun and its planets are like a tiny raft in this cosmic river, carried along by the Milky Way's gravity. The worst we'd experience: a radically reshaped night sky where Andromeda stars smear across the heavens like glitter tossed into a whirlpool. Over billions of years, the two galaxies will settle into a new shape, likely a giant elliptical galaxy some astronomers are already calling Milkomeda. Yet for all the violence of the merger, the real drama happens not with stars but with gas. Unlike stars, the thin clouds of hydrogen between them do collide, compressing and igniting bursts of new star formation. Some simulations show brilliant blue arcs of young stars lighting up like fireworks at the edges of the merging galaxies. That's where the true destruction lies, not in stellar smash-ups, but in the rebirth of stellar nurseries from the wreckage. So if you're worried about cosmic car crashes, relax. The universe is too spacious for chaos. Even in the heart of a galactic collision, nature keeps its distance, reminding us that emptiness is the rule, not the exception. And when Milcomda finally forms, Earth, if it still exists, will have a front row seat to the most beautiful demolition derby the cosmos has ever staged. Jupiter doesn't just dominate the solar system with its size, it screams its presence across the cosmos in a language of crackling radio waves. If you could tune a receiver to the right frequency, the giant planet's voice would flood your speakers with eerie wails, whistles, and pops, sounding less like a world and more like some haunted transmission from deep space. These aren't random noises, they're decametric radio bursts, a symphony of electromagnetic chaos born from Jupiter's crushing magnetic field and the tortured dance of its volcanic moon, Io. The Juno spacecraft, orbiting Jupiter since 2016, has captured these radio storms in spine-tingling detail. Played back at frequencies audible to human ears, they resemble the static of an old analog TV mixed with ghostly howls, a soundscape so unsettling NASA once released it as a Halloween treat. But the science behind these emissions is even wilder than the audio. Jupiter's magnetic field is a monster 20,000 times stronger than Earth's, stretching so far that if it were visible, it would appear larger than the full moon in our sky. When Io, the most volcanically active body in the solar system, orbits through this field, it acts like a cosmic generator. Sulfur and oxygen ions blasted from Io's volcanoes become trapped in Jupiter's magnetic grip, creating a rotating donut of charged particles called a plasma torus. As this torus plows through Jupiter's magnetosphere at over 45,000 miles per hour, it generates million-amp electrical currents that spiral along magnetic field lines, ultimately crashing into Jupiter's poles like an invisible lightning storm. The result, auroras so massive they could swallow Earth whole, and those eerie radio bursts that echo across 500 million miles of space. Unlike Earth's northern lights, which shimmer silently, Jupiter's auroras roar across the electromagnetic spectrum, firing off radio waves like a celestial distress signal. Amateur astronomers with simple radio telescopes can actually pick them up. Jupiter's storms are one of the few cosmic phenomena audible from backyard setups. But here's the twist, these radio bursts aren't constant. They pulse in rhythms tied to Io's orbit, flaring up when the moon is at certain points in its path. It's a real-time demonstration of celestial mechanics, where gravity, magnetism, and volcanism conspire to create something both beautiful and bizarre. And while the sounds might send chills down your spine, they're also a reminder that the universe is anything but silent if you know how to listen. Jupiter's radio storms are more than just cosmic noise pollution. They're a window into the invisible forces shaping our solar system, a reminder that even the quietest-looking dots in the night sky can be screaming into the void. And somewhere in those crackling signals, there might be clues to how other planets, both here and around distant stars, hum their own electromagnetic tunes. So next time you gaze at Jupiter, remember, it's not just a planet, it's a broadcaster sending messages in a language of charged particles and magnetic fury. All we have to do is tune in. What if everything you see, touch, and experience is nothing more than an incredibly convincing projection, like a cosmic illusion painted onto the fabric of reality itself? This isn't the plot of a sci-fi movie. It's a serious scientific idea called the holographic principle, and it suggests our three-dimensional universe might actually be encoded on a two-dimensional surface at its edges, like a movie projected from the rim of existence onto the screen of our perception. Think of it like the pixels on your phone. Up close, an image looks smooth, but zoom in far enough, and you'll see the tiny dots that construct it. The holographic principle argues space-time might work the same way, that if you could peer deep enough into reality's architecture, you'd find it's made of fundamental bits of information etched onto some distant boundary we can't perceive. This idea didn't come out of nowhere. It grew from attempts to solve one of physics' most frustrating puzzles, the black hole information paradox. When matter falls into a black hole, it seemingly vanishes forever, violating quantum mechanics' rule that information can never be destroyed. But in the 1970s, physicist Jacob Bekenstein calculated that black holes encode information about what they swallow not in their voids, but on their surfaces, their event horizons. Like a cosmic hard drive, every bit of data about an ingested star gets imprinted onto this two-dimensional boundary. Stephen Hawking later showed these horizons can slowly leak radiation, causing black holes to evaporate over eons. But if the information stays preserved on the surface, it could theoretically be recovered, solving the paradox. This revelation sparked a wild thought. If black holes store 3D information on 2D surfaces, could the entire universe work the same way? The mathematics says yes. Imagine reality as an enormous hologram, where every event, every particle, every law of physics is just a projection from data stored at the cosmic horizon, the edge of the observable universe. Your hands, the stars, even time itself would be shadows cast by this deeper, flatter reality. Scientists aren't just philosophizing about this, they're hunting for proof. At Fermilab, the holometer experiment fires lasers down long tunnels, searching for telltale jitters in spacetime that would reveal its pixelated nature. Other teams analyze cosmic microwave background radiation for anomalies that might hint at an underlying code. So far, no smoking gun, but the search is young. Here's where it gets trippy. If the holographic principle is real, it means free will, time, and even consciousness could be emergent properties of this information processing. Like characters in a video game unaware they're made of ones and zeros, we might be living in a universe that's fundamentally data, not solid, not material. Just math made manifest. Whether the universe is a hologram or not, the mere possibility reshapes how we see existence. It blurs the line between science and philosophy, forcing us to ask, what is reality really? And if we're just projections, what or who is holding the projector? If black holes are the universe's ultimate one-way streets, white holes could be their bizarre cosmic counterparts, flinging matter outward instead of devouring it, like a fire hydrant blasting water into space at the speed of light. These theoretical oddballs emerge straight from Einstein's equations, mathematical mirror images of black holes where event horizons become exit-only doors. Nothing gets in, everything gets out. Not even light can backtrack through the cosmic turnstile. Picture a black hole running in reverse, instead of a crushing singularity hidden behind an inescapable boundary. A white hole would erupt with the energy of swallowed stars, violently expelling everything that ever fell into its darker twin. Some models even suggest they could be connected wormholes stitching together the two extremes, with matter sucked into a black hole only to be vomited out a white hole elsewhere in spacetime. It sounds like science fiction, but the math doesn't lie. White holes are just as valid under general relativity as black holes, at least on paper. Here's where reality gets messy. While black holes form naturally from collapsing stars, white holes would need to defy thermodynamics, somehow reassembling crushed particles back into ordered structures. Imagine taking a shattered vase and flinging its pieces into the air only for them to spontaneously reform mid-flight. That's the level of cosmic rewiring required. Plus, we've never spotted one. No gamma-ray burst, no anomalous jets of ancient matter, just eerie silence where these cosmic fountains should be. Yet the idea persists in part because it solves puzzles. Could the Big Bang itself have been a white hole, birthing the universe in a single explosive event? Some theorists speculate that quantum loops in spacetime might briefly spawn microscopic white holes, flickering in and out of existence like quantum foam bubbles. Others wonder if they're hiding in plain sight. Maybe quasars, those brilliant galactic cores, are white holes in disguise, their dazzling jets actually matter escaping another reality. Science fiction loves them, of course. From Doctor Who's regenerating TARDIS to Event Horizon's nightmare portal, white holes symbolize cosmic rebirth or terrifying leakage between dimensions. But real physics remains stubbornly silent. Perhaps they're just mathematical ghosts, shadows cast by equations pushing beyond their limits, or maybe we haven't looked hard enough. After all, black holes seemed equally absurd until we photographed one. Until then, white holes linger at the edge of possibility, a reminder that the universe's rulebook might still have pages we haven't turned. Whether cosmic exhaust valves or beautiful dead ends, they challenge us to imagine a reality where even the strictest cosmic laws might have an escape clause. Every piece of gold you've ever touched, the ring on your finger, the wiring in your phone, even the fillings in your teeth, was forged in the heart of a cosmic catastrophe so violent it makes supernova look tame. These precious atoms weren't born on Earth. They didn't even come from our sun. They're the scattered remains of two dead stars crashing together in a fleeting, cataclysmic embrace, an event so rare and powerful, astronomers call it a kilonova. Let's rewind to August 17, 2017. Gravitational wave detectors LIGO and Virgo picked up ripples in spacetime, the telltale signature of two neutron stars, each heavier than our sun but no wider than Manhattan, spiraling toward oblivion. As they collided, the universe briefly flashed brighter than a billion suns, ejecting a firestorm of heavy elements into the void. This event, catalogued as GW 170817, wasn't just the first confirmed kilonova, it was a Rosetta Stone for decoding where Earth's gold, platinum, and uranium actually come from. Here's the staggering math. That single merger produced roughly 10 times the mass of Earth's entire gold reserves. Picture a sphere of solid gold the size of a small moon, vaporized into a glowing cloud and scattered across the galaxy. Over billions of years, some of those atoms drifted into the molecular cloud that birthed our solar system, eventually condensing into asteroids and finally raining down on Earth during the planet's violent infancy. But kilonovas aren't just gold factories. They're the universe's ultimate alchemists, forging elements so heavy they can't form in ordinary supernova. When neutron stars collide, their absurd densities, a teaspoon of their material weighs as much as Mount Everest, create conditions so extreme. Protons and electrons get crushed together into neutrons, then rapidly capture additional particles in a process called R-process nucleosynthesis. The result, a periodic table's worth of exotic elements sprayed into space like cosmic shrapnel. Yet for all their destructive power, kilonovas are vanishingly rare. The Milky Way might host one every 100,000 years. That's why Earth's gold is so scarce. It's literally stardust from the universe's most exclusive disaster. Next time you hold a gold coin, remember, you're gripping condensed starlight, a relic of two dead stars that died screaming in the dark, just so their shattered atoms could one day sparkle in your hand. This revelation rewrites our origin story. We're not just made of stardust, we're made of collision dust, the fallout of the cosmos's most extreme reunions. And somewhere out there, another kilonova might be brewing, minting future treasure for civilizations not yet born. On August 15, 1977, a radio telescope in Ohio picked up a signal so bizarre, the astronomer reviewing the data circled it in red ink and wrote a single word in the margin: "Wow." That hastily scribbled note would become the name of one of astronomy's greatest unsolved mysteries, a 72-second burst of radio waves that matched exactly what scientists predicted an extraterrestrial transmission would look like. The signal came from the direction of the constellation Sagittarius, blasting at a frequency of 1,420 MHz, a quiet channel where cosmic noise is minimal, precisely the sort of spot an advanced civilization might choose to send a message. It was narrowband, meaning it wasn't natural static but a focused transmission, and it was loud, 30 times stronger than the background hiss of space. Most tantalizing of all, it drifted slightly in frequency, just as a signal from a rotating planet would. For those 72 seconds, it seemed like we might have finally found proof we weren't alone. Then, as suddenly as it appeared, it vanished, despite decades of follow-up searches, including sweeping scans with more sensitive telescopes. The signal never repeated. Not once. It's as if the universe teased us with a single, cryptic postcard before retreating into silence. Theories abound: a passing comet's hydrogen cloud reflecting Earth's own radio leakage, a military satellite's classified transmission, or the electrifying possibility, a fleeting hello from a civilization that switched off its beacon or worse, perished before we could reply. Modern SETI projects like Breakthrough Listen have revived hope, armed with AI and telescopes 1,000 times more powerful than 1970s gear. They've scanned the WOW. Signal's origin point down to the atomic level, yet the silence holds. But here's the twist: we're not just listening anymore. Efforts like METI, messaging extraterrestrial intelligence, actively beam replies toward the WOW. Signal's coordinates, a cosmic hello flung into the dark. Whether it's bravery or folly depends on who you ask. Some warn against advertising our presence, while others argue curiosity is too fundamental to suppress. The WOW signal endures because it's the perfect cosmic riddle, too precise to dismiss, too fleeting to confirm. It's a reminder that the universe might be shouting at us in a language we're only beginning to decode. And until we hear it again, or never do, it remains the closest we've come to feeling the gaze of another intelligence staring back. Far from the sun's warmth, in the frozen outskirts of our solar system, Saturn's moon Titan hides a landscape that feels hauntingly familiar, yet alien beyond imagination. Here, liquid methane and ethane cascade into vast lakes and seas, carving river valleys and pooling into basins with shorelines that mirror Earth's coastlines. When NASA Cassini spacecraft pierced Titan's thick, orange haze in 2005, its radar didn't just find scattered puddles. It unveiled an entire hydrologic cycle, complete with rain, evaporation, and waves, except instead of water, it's all powered by hydrocarbons. This isn't just another icy moon. It's a looking-glass version of Earth where the rules of chemistry rewrite what life could look like. Picture standing on Titan's frigid shores, where temperatures hover around -290 degrees Fahrenheit. The sand beneath your boots isn't silica, it's organic compounds ground into granules by methane rivers. The waves lap at your feet, but they're sluggish, thickened by the cold, moving in slow motion compared to Earth's ocean surf. Cassini's observations even hinted at transient islands, perhaps bubbles of nitrogen gas or floating clumps of hydrocarbon sludge, drifting across these alien seas. The largest Kraken mare stretches wider than the Caspian Sea, its depth still uncharted, its mysteries still untouched. Now for the tantalizing question: could life swim in these methane lakes? Earth's extremophiles, organisms thriving in boiling vents or acid pools, prove life adapts to the unlikeliest conditions. Titan's chemistry offers a parallel playground. Instead of water as a solvent, methane could fill that role with complex molecules like acrylonite, while forming cell-like structures in labs. These hypothetical azotosomes wouldn't need oxygen. They'd metabolize hydrogen and acetylene, both abundant on Titan. It's a radical reshuffling of biology's deck, where life might look less like fish and more like we can't even guess. Enter Dragonfly, NASA upcoming drone mission set to launch in 2027. This nuclear-powered marvel will hop across Titan's dunes and lake beds like a robotic dragonfly, sampling organic sludge and sniffing the air for chemical imbalances that hint at biological activity. Its target, the Selk Impact Crater, a site where liquid water may have briefly mixed with Titan's organics, a potential crucible for probiotic chemistry. Dragonfly won't just photograph this alien world, it'll taste it, probing for the molecular whispers of something stirring in the dark. Titan's methane seas are more than a scientific curiosity. They're a testbed for the universality of life's principles. If biology can spark in such a frigid, alien landscape, what does that say about the cosmos's creative potential? Whether Dragonfly finds microbes or just more questions, one thing's certain: Titan is a mirror held up to Earth, showing us how narrow our definitions of habitability might be. And in its icy depths, it may hold the keys to life's most profound secret, that it flourishes not in spite of the universe's harshness, but because of its boundless ingenuity. The coldest thing in the universe isn't some distant nebula or the void between galaxies, it's all around you, right now. A faint, near-uniform glow that permeates every cubic inch of space, the last embers of creation's fire. This is the cosmic microwave background, the afterimage of the Big Bang, cooled to just 2.7 degrees above absolute zero, minus 454 degrees Fahrenheit. It's not just background noise, it's the universe's oldest light, stretched and dimmed over 13.8 billion years into a whisper of microwaves, a ghostly echo of when everything was smaller, hotter, and unimaginably denser. But this frigid glow holds staggering secrets. When satellites like Kobe and Planck mapped its minute fluctuations variations as tiny as 1 part in 100,000, they were essentially decoding the universe's baby pictures. Those faint temperature ripples aren't random. They're frozen sound waves from the cosmos's first 380,000 years, when it transitioned from opaque plasma to transparent gas. Picture the early universe as a simmering soup of particles, with regions slightly denser than others. Gravity pulled matter toward these knots, while radiation pressure pushed it away, creating oscillations that literally ring through space-time. The patterns we see today are like fossilized echoes of those first cosmic drumbeats. Here's the magic: those infinitesimal wrinkles became the blueprint for everything. The slightly warmer spots, they're the seeds of galaxy clusters, regions where extra mass eventually collapsed into the vast structures we see today, the cooler patches. Cosmic voids, the empty stretches between the threads of the cosmic web. Without those primordial imperfections, gravity would have had nothing to work with, and the universe would be a featureless sea of particles. Our existence hinges on those microscopic fluctuations, baked into the fabric of reality before stars or atoms even formed. The precision of this snapshot is mind-bending. Planck's map reveals details down to scales of 1 part in a million, like discerning individual raindrops in a hurricane from billions of years away. Yet even this razor-sharp image has gaps. The cosmic microwave background's polarization, subtle twists in its light, hints at inflation, a theoretical faster-than-light expansion in the universe's first sliver of a second. Some patterns in the data might even point to other universes, their gravitational tug warping our own like fingerprints pressed against glass. What's most humbling is how this cold, ancient light connects us to the dawn of time. Every photon hitting a radio telescope today began its journey before Earth, before the Milky Way, before the first stars ignited. It's a message in a bottle from the universe's infancy, telling us not just where we came from, but how fragile our cosmic architecture really is. And like any good mystery, the closer we look, the more questions arise. Why is one half of the sky slightly warmer than the other? What caused the mysterious cold spot that defies standard models? The cosmic microwave background isn't just a relic, it's a puzzle box, and we've only just begun to turn the key. Einstein famously called it spooky action at a distance, a phrase dripping with both awe and skepticism. Quantum entanglement, the bizarre phenomenon where two particles become inextricably linked across vast cosmic gulfs, defies everything we know about space and time. Imagine taking two coins, flipping them on opposite sides of the galaxy, and always getting matching heads or tails no matter how far apart they are. That's the level of cosmic coordination we're dealing with here. When entangled particles are measured, their properties sink instantaneously, as if the universe itself forgot to put distance between them. The implications shatter conventional logic. In labs today, scientists routinely entangle particles and separate them by hundreds of miles, and the correlation holds. Photons fired through fiber optic cables or even between satellites maintain their ghostly connection, with measurements on one instantly determining the state of the other. This isn't mere theory. It's been verified countless times, most spectacularly in 2017 when Chinese scientists used the Mishi satellite to entangle photons over a record-breaking 720 miles. The results, perfect harmony, as if the particles were whispering secrets across continents faster than light could traverse the distance. So how does this rewrite the future? Start with unhackable communication. Quantum encryption exploits entanglement to create keys that change the moment they're observed by an eavesdropper. Any attempt to intercept the message collapses the quantum state, leaving a glaring fingerprint of tampering. Governments and banks are already racing to deploy this tech, with China launching the world's first quantum-encrypted satellite network. But the real moonshot is quantum teleportation, not of people or objects, but of information. By entangling particles and carefully manipulating their states, researchers have teleported quantum data across labs and even between ground stations and orbiting satellites. The process doesn't move matter, it transfers the exact quantum configuration of one particle to another, like faxing the soul of an atom. Yet the deepest mystery remains how entanglement works. Some theories suggest particles are connected through hidden dimensions or that the universe is fundamentally non-local, with everything secretly touching everything else. Others propose that at the quantum level, cause and effect don't follow strict timelines, meaning the particles might not be communicating at all, but simply existing in a state where their fates were always intertwined. This isn't just physics, it's philosophy. Entanglement hints that reality might be a vast, interactive hologram where separation is an illusion and the universe is far more interconnected than we ever dreamed. And as we harness this phenomenon to build quantum computers and star-spanning networks, we're not just advancing technology, we're peering into the cosmic rulebook and finding pages we didn't know existed. What if everything, the stars, the laws of physics, even the thoughts in your head, were nothing more than lines of code in an unfathomably advanced simulation? Philosopher Nick Bostrom's famous trilemma presents this possibility with unsettling logic. His argument boils down to three stark options. Either intelligent civilizations never reach the technological capability to create realistic simulations, they choose not to run them despite having the ability, or we're almost certainly living inside one right now. Given the trajectory of our own tech, from crude video games to rudimentary VR, that first option feels increasingly unlikely, while the second seems improbable for a species curious enough to build particle colliders and space telescopes. That leaves the third, a statistical near certainty that we're someone else's digital experiment. This isn't just sci-fi musing, it's a framework that reframes the Fermi paradox. If the universe is teeming with civilizations, why haven't we heard from them? One chilling answer: they're busy running ancestor simulations, recreating their evolutionary past inside quantum supercomputers. Earth's entire history might just be an academic project for post-biological beings studying their origins. Some theorists even suggest glitches in reality, like déjà vu, quantum indeterminacy, or the Mandela effect, could be artifacts of imperfect rendering, cosmic typos in the source code. But can we test this? Physicists have proposed hunting for literal pixelation in space-time minimal length scales where reality might snap to grid under extreme magnification. High-energy particle collisions could reveal if energy disperses in discrete chunks rather than smooth gradients, hinting at underlying computational limits. Others suggest looking for mathematical shortcuts in nature constants like the speed of light might be processing constraints keeping the simulation from lagging. Even quantum superposition, where particles exist in multiple states until observed, echoes a video game's resource-saving tactic of only rendering what players actively see. Yet the simulation hypothesis isn't just about glitches, it's about purpose. If we're simulated, are we lab rats in some cosmic experiment, players in a civilization-scale game? Or worse, forgotten background characters in an abandoned project? The unsettling beauty of Bostrom's trilemma is that it forces us to confront not just the nature of reality, but the fragility of our place within it. Whether we're base reality or someone's elaborate simulation changes nothing about our lived experience until the day we find evidence otherwise. And that search for cracks in the cosmic facade might be the ultimate scientific quest of all. From invisible dark matter shaping the cosmos to diamond planets worth more than every earthly treasure, combined, our journey through the universe's strangest truths has revealed a reality far wilder than fiction. We've wandered through the shadowy halls of quantum foam, where spacetime itself flickers in and out of existence, and glimpsed the eerie geometry of Saturn's six-sided storm, a hurricane so precise it defies nature's usual chaos. We've grappled with the holographic principle, the spine-tingling idea that everything we see might just be a cosmic projection, a 3D illusion encoded on some distant 2D boundary. And who could forget the great attractor, that mysterious gravitational puppeteer dragging entire galaxies toward an unseen fate? But here's the thing, these aren't plot twists from a sci-fi novel. They're real, measurable phenomena, each one a testament to just how little we truly understand. The universe doesn't just tolerate mystery, it thrives on it, dangling riddles like cosmic breadcrumbs to lure us deeper into the unknown. For every answer we uncover, like the kilonovas that forged the gold in your jewelry or the entangled particles whispering secrets across light years, a dozen new questions erupt in its place. Carl Sagan once said, "Somewhere, something incredible is waiting to be known." And he was right, whether it's the true nature of dark energy hurtling galaxies apart or the faint whispers of a wow signal from some distant civilization, the cosmos is brimming with enigmas that refuse to be neatly solved. That's the magic of it all, not just the answers, but the endless pursuit of them. So keep looking up, stay curious, and if you're hungry for more mind-bending cosmic wonders, don't forget to like and subscribe, because the universe isn't done surprising us yet, and neither are we. The next revelation is always just a starry sky.